Okay, so hello dear students. So this is the continuation of our lecture. So this is a brand new lecture, and before we start the lecture 2, I'd like to give you some couple of informations that will be helpful to those of you doing the labs. So on the release of this video, which is probably the 2nd of November, you'll have your first lab, and you have all the information that you require on the USM. So just look around and you find information on the labs. So we'll just get right into our and also for the lectures, those of you that are doing it online, just watch the videos, and if you have any questions, contact me, and watch the videos taking notes. Please do take notes. And by the way, I can monitor the track the videos or the progress of the videos online, so it's not accident that I'm putting it through YouTube or something. So let's just go into the lecture. So here we are doing the second part, the first part of the first lecture, as you saw earlier. So we're doing atoms, molecules, and ions. So before we start, as usual, I will ask the question: what is atom? What is an atom? What are atoms? And you give the answer, and then I'll continue. Yeah, as usual, you just pause the video and then ask yourself in your room or wherever you are, what are atoms, and think about it deeply before you progress with the video. So let's get right into it. So in this part, we're going to be looking at the atoms, atomic theories, components of atom, quantitative properties of the atom, introduction to the periodic table. We want to know what the periodic table is, molecules and ions, formulas and ionic compounds, the name of compounds as well. So this is what we're going to be doing quickly in this part. So atoms basically are building blocks of chemistry. If you see a building is made up of not just the foundation. Remember, we talked previously about chemistry being the foundation of all other courses, and atoms are like your building blocks. You need a block to raise a building, and matter is anything that has mass and occupies space, and this matter made up of atoms. And these atoms are the constituents of elements. They're the reacting particles of an element, and you have it stacking up. Well, to focus on matter is made up of electrons, protons, and neutrons. That's what the matter is made up of. Well, it stands alone. And I think in the class I was talking about the word called tomos. STOMOS. The word tomos it means to cut. Then when you say atom, anything you add an A to, it negates it. It means not cut. So you have an atom. Atoms are made up of electrons, protons, and neutrons. And you have molecules, which are the building blocks of elements and compounds. Then you have ions, which are charged, the oppositely charged particles that are present in compounds. So an ionic compound can have a positive and a negative side to it. So we're speaking now on the atoms and atomic theories. So notice that I think I asked this question in the class as well. I want you guys to think about what theories are, so that you better understand that these individuals or the theories we're going to be looking at were postulated on the basis of them not having any clue as to what atoms really are. So now we know what they are. So when we're reading the theories, we'll be reading it with some foreknowledge. But they were researching to come up with all these theories that they came out with. So it's quite important you know it as such, because if I'm telling you about a phone and you have a phone, you already will be like, yeah, I know that already. But when very few people have this understanding and it's being talked about, it will be quite enlightening. So John Dalton is an Englishman. He came up with the atomic theory, and his theory is quite interesting. He said an element is composed of tiny particles called the atom. Notice the word tiny particles. And in an ordinary chemical reactions, atoms move from one substance to another, but no atom of any element disappears or is changed into an atom of another element. Very important. Use the word disappears or is changed. So those two things don't happen. And he concludes by saying an atom is the smallest reacting particle of an element. Very important. The atom is the smallest, keyword, reacting, very important, particle of an element. So those four elements are very important when you're trying to explain what an atom is. And then you can include the fact that it's made up of electrons, protons, and neutrons. So that's how you define an atom. So this is an image to explain graphically what Dalton was trying to say. You have element 1, which has atoms of that element 1. See it here with the color blue. And then you have another element 2, atoms of element 2 with the color red. And then you have a combination to form a compound, another combination to form another compound. And it says different combinations produce different compounds. Very important. And then he now says this element 1 and 2 we also have different masses. So it means they are very different, not just in looks, they are also different in how much they weigh. So as several elements, they will weigh differently. The important thing now is when they react, when you add 2 of element 1 with 1 of element 2 together, you have this, which is very much the compound 1. Notice that he said 2 other things doesn't happen. You can't put 2 of element 1 and end up losing 1 of that element 1. Or you can't have element 2 change, or even element 1 change. So no change, no form of disappearance can happen, no form of change can happen. What you add at this end is what you receive at the other end. And I always say this to the students. You can't go to the market and prepare to cook rice. You bought the rice, you put it on the fire, and you open the pot when you're cooking and you see beans. It doesn't happen. What you put together is what you get. So very important. 2 things. John Dalton says it doesn't disappear, it doesn't change. So what you add together is what you get at the other end. So very important that we know that. Then we now explain what electrons are. So we said first evidence of subatomic particles came from the study of the conduction of electricity by gases at low pressure. So the word subatomic, let me explain. I say anything sub is under or inside, something like that. So the subatomic particles, electrons are subatomic particles. They're found in the atom, so they're called subatomic particles because atoms themselves are particles. So if they're inside particles, they're subatomic particles. So and this is explained with the cathode ray apparatus. And I want to go ahead to show us what it is and then come back a little bit and further explain. So this is what the cathode ray apparatus look like. If you were to think of something that's very close or imaginary, because it might not look like it in this image, is your tube, your fluorescent tube. If you have a fluorescent in your room, it's a fluorescent tube. So you have your cathode end, which is your negative, and you have your anode end. And then you have a coil jacked in through it. And then there's what you have called your zinc sulfide screen, and it's kind of like your detection screen that you use to see the whole flow of the electron and how it bends towards the positive, because it's negative, so it tends towards the positive. And that's what the goal of the experiment was, to prove that the electrons are negatively charged. So the sulfide screen you will see later on in our next image that we'll have somewhere in front with N.S. Rutherford's experiment as well. So let's go back. So this is all explained. Remember, it's in a tube. Even the way your bulb is in a vacuum where you don't have anything external reacting with it, that's how the bulb works. So you have that, and the resultant is the electric current. And look very closely, the word electricity and electron, if you look, the only difference is I and city, and electron is almost like, electricity is almost like a city of electrons where charges are moving all through the cables, and you collect yours when you turn it on. And I make jokes in the class with people that plugs their phones and they forget to turn it on, so electricity doesn't flow from the cable to the phone. So you wake up in the morning and your phone is still 5%, and you're wondering why your phone is 5%, because you actually didn't allow the city of electrons to flow into your phone to charge it up. So the cathode ray is basically composed of the negatively charged particles called the electron that flows through it. And then it goes further to say that electrons carry a unit negative charge and have a mass approximately 22,000. The light has atomic mass. So it has we'll see the mass as we go ahead. So this is the image, we've explained it. So we have fundamental laws of matter. Like everything, you have laws governing them. So first is the law of conservation of mass. It means that there's no detectable change in mass in an ordinary chemical reaction. What this simply means is that when you react two things together, if one is 5 grams, the other is 5 grams, if you add them together, what should you get at the other end? 10 grams. So you don't have a detectable change in mass when you react both of them together. Notice that it's conservation of mass. The word conservation means you are retaining something as you move. You are trying to conserve, you're trying to protect something. And then you have the law of constant composition. The names of the laws are very much self-explaining what the law is about. So when you say constant composition, so it simply means that an atom always contains the same elements in the same proportion. Remember, constant composition. That means the composition will always be constant through. So it's the same elements and the same proportion. Take for example water. It's H2O, so it's going to be 2 to 1. Every time you see it is 2 to 1. The proportion might increase, but it will be 2 to 1. So you have another law of multiple proportions, very close to the first, but slightly different. It says that masses of one element that combine with the fixed mass of the second element are in the ratio of small whole numbers, not fraction. Remember, the example of water is 2 to 1, not 1 to 1.5. That's a fraction, not a whole number. So it can be 2 to 1, which if you put a 2 in front of H2O, which will look like 4 to 2, it just be the proportions can multiply, but it has to be whole numbers. So we have an example of two different oxides of chromium and chromium. Who can tell me what the symbol for chromium is? Okay, I can hear some people just saying it and some people not knowing what it is. So the symbol for it is Cr. That's just a joke. I didn't hear anybody saying anything. I'm just assuming you did if you're good with your periodic tables. So Cr is a symbol for chromium. It's not C, it's not CH, it's Cr. So the two of them are different on the basis of the amount of oxygen in them. And I think anytime I explain this as this. Oxygen basically is what we have around about us in the air, and it's what results in spoilage. If you keep exposing, if something's out for too long, it gets oxidized, and it can result in spoilage if continuous oxidation takes place. That's why you put things in the refrigerator. When you put them in the refrigerator, you tend to drop down the oxygen level and reduce the spoilage, because your refrigerator runs on a gas which is basically nitrogen, and liquid nitrogen, if you know liquid nitrogen, is quite frizzy. I think not so far from today they did a Halloween. When you want to give a spooky feel, you have all those smoke and steam. If you watch movies where steam comes, it's basically liquid nitrogen or some fume. They used to use either steam or the liquid nitrogen that's more catchy, because you see the whole thing coming out. The same feeling when you open your freezer in the house, you see the fume coming out, that kind of feel. So the gas at behind is what ensures the fridge runs effectively. It's released in bits. If you have the real one in a bottle, you'll see what I'm talking about. Some of you can just Google it and then you see what I'm talking about. But when you come to this, even rust and some of the things that happens, the reason why metals are coated is to avoid oxidation. If you have your apple, you slice it, you can quickly see the color change very quickly if you leave it. So what you can either do is to put it in water or put some vinegar on it. Any which one will slow the process of oxidation, just to explain that oxygen can literally make a difference, as you can see obviously with the two chromium. So we have the next model, which is a theory postulated by J.J. Thomson. If you are watching this and you're looking and you're wondering what you see, is actually bread. It's not an accident. I have bread. So J.J. Thomson actually got his own model from the raisin pudding, the plum pudding or the raisin bread, and it's called the plum pudding or the raisin bread model. So it means that you can get your ideas for your theories from the kitchen or from food. So nobody has a restriction on these things. So J.J. Thomson actually proposed that the atom is a positively charged sphere, and then within the sphere you have the electrons, which are the raisins. I hope everybody knows what raisins are. Raisins are basically dried grapes. So you have the raisins and then the bread itself. So that's what his model was basically about. And then we move quickly to Ernest Rutherford. So notice we started with John Dalton, J.J. Thomson, and then now we're looking at Ernest Rutherford, who developed the fundamental ideas on the nature of the atom. And his is quite profound because we're looking at the protons and the neutrons. And he introduces us to a thin gold foil, which he bombards with alpha particles. And then he noticed something very interesting. Let me show us the image very quickly. Yeah, this is what it is. So he actually used, and this ring you have is zinc sulfide that I told you of before, and he bombards the gold with the thin gold foil with alpha particles, the kind of your electron. And then he notices something happens. This is what he expected to happen, but he notices that things were bouncing off, they're deflected in some sense, which gave him an idea that there's something happening there, which I want you to guess. Some of you might not even bother, but in reality, it's the neutrons and the protons at the center that were causing the whole bounce to happen, or the whole deflection to happen. In fact, some of them even go backwards, to tell you that they just hit and really move straight backwards. So that was his. Let's just walk through. So the fluorescence basically used to examine the extent of the scatter. So what was happening is a scatter, deflection, and it would involve using mathematical analysis, and then he concludes that the nucleus is actually positively charged. Nucleus property, and we know that what makes the nucleus positively charged is the presence of the protons, because the protons are positively charged particles, while the electrons are negatively charged, but they are not in the nucleus, they are outside. But you have the neutrons, which are neutrally charged, and they're also as well. They have a weight that is higher than that of the protons. So you have that. This is the definition. So the neutrons of the atoms are to be considered as particles, because they are all, the nucleus of the atom is considered as particles because they have particles in them. So you have the protons, which is a unit positive charge, and with a magnitude to that of the electron. So the magnitude there is kind of like the force to that of the electron. And the neutrons are uncharged particles, which has a mass slightly greater than that of the proton. So the mass of the neutron is greater than that of the proton, and then you have the magnitude of the proton similar to that of the electron. So it's force and then mass. So notice that things can be small, but they have a good large force. So force is not bound to size. You can see big people that punch harder than small people if you're looking at boxing and all the other sports that we have around, because small people do awesome things as well. So it's not bound to size or anything. So we see it graphically, or we see it in a table. Protons are located in neutrons. Neutrons are located in the nucleus. Sorry, I made a mistake. Protons are located in the nucleus. Neutrons in the nucleus as well. Electrons are outside. So it's +1 for proton, 0 for neutrons, and -1 for electron. And here are the masses. So you see the difference. Notice the electron 0.0055. That's for an electron. And then the proton is this, and then you notice the difference between the two. So this neutron is higher. So you have this image I've explained before, and then I will go to this part where we talk about the quantitative properties of an atom. Then we start off by explaining the atomic number. The atomic number is like your student number. Your student number, no two students have the same student number. So no two atoms will have the same atomic number, and it's denoted Z. Don't confuse it for A, because it seems like atomic number should have been A and mass number should have been Z. No, it's the reverse. So Z is what is used to denote the atomic number, and it's the number of protons present in the nucleus of a substance. Notice that we use the number of protons for a reason, because the protons is in the nucleus. It cannot change, the electrons can change. So that's it for that. Just quickly go down to the mass number. So the mass number is denoted A. So the mass number of an atom is the sum of the protons and the neutrons in the nucleus. So when you're trying to weigh something, you want to weigh the whole of it, because the electrons are moving around and they're very light. So what is weighed is the core, which is consisting of the protons and the neutrons. And it's very important that you understand that the A is your Z plus the number of neutrons. So if we've known that, we now move to the concept of isotope or isotopy. Let me just do it like this. With human beings, if you have two people that look very much alike, that were given birth on the same day, you call them twins because they look very much alike. Sometimes some of them are identical, some of them are unidentical, but the ones that are identical is what I'm talking about. We call them twins. And obviously they're twins. So with atoms, when you have a situation where two of them look alike, you call them isotopes. So that's kind of like your atomic way to look at twins. When the human way to look at them is to call them twins, the atomic way to look at them is to call them isotopes. So atoms that possesses the same number of protons, which makes them give them the same atomic number, and then different number of neutrons are called isotopes. So I noticed that with twins, two of them can look alike. One, it will never be the same exact weight. You will rarely, because one will eat more than the other, and they will be different in character. That means one can talk more than the other. You always will have differences on the basis of twins. So the same way we work on the differences. Differences is based on their weight, which is their number of neutrons. So you have one being more than the other, having the same number of protons but having different number of a different mass number, because once you add the protons and the neutrons, you have the mass number. So we go to what we call the nuclear symbol. In the last lecture, or the last lecture, we talked about atomic symbol, but now we'll look at nuclear symbol. In the nuclear symbol, note the word nuclear has to do with the word nucleus. So it means that you're not adding the contents of the nucleus to the atomic symbol. That is basically what it is. So the example we have above here is your uranium, and most of you know what uranium is. If you watch movies, it's a radioactive element, and on the basis of the differences, notice that U is the symbol, the atomic symbol, so you write it down, and then in this case, which is the first one, is 235. That is the mass number. Is the mass number, and it's denoted A. And then downstairs here is your atomic number. So notice that the way you write the symbols is your atomic number is written as a subscript to the left of the element, on the right, left of the element, and you see it as a subscript. The word subscript means that it's under or it's inside, just under. So you have that written here. That is the atomic number, and then the mass number is written as a superscript at the upper left. So it's here. Super means it's in the air. Anything super flies. Anything sub is under, submarine, and all of those things. So you have that here, and this is the whole thing. So it means that if you are to use letters, you have this being X to symbolize any of the element, and then what will be above will be A, and what will be below will be Z. So it's A to Z. A in the air, Z beneath. So that's how you write your nuclear symbol. Then we have an exercise to do, and I think it's after this exercise we'll end this part. So the exercise is such that you have an isotope of antimony. So, and this isotope of antimony is the word antimony is the name antimony is very different from the atomic symbol. So notice that the atomic symbol is Sb, and if I was to ask you a question, why is it Sb? What makes the difference? Why does it become Sb? It should have been At or Ay or An. Why is it Sb? Ask yourself that, or tell me the answer. Okay, let me just say quickly. The reason for that is because it's named from the Latin name, so the symbol is gotten from the Latin name. So it's stibium, and then you have Sb from the Latin name. So, and its atomic number is 51, and it says it's used as a tracer to detect leakages or leaks in oil pipelines. So they use this to detect leaks in oil pipelines. So if there are leaks, the antimony is what is going to be used to detect it. So this isotope has 73 neutrons in its nucleus. So what is the nucleus symbol? So that's the question. What is the nucleus symbol? So obviously you can write your Sb and then start fixing the values. So I would like you to do that quickly before we resolve. So just pause the video and take your time to resolve it, because I've explained what it is. We use uranium to do the explanation. So pause the video and do it quickly. What are you waiting for? Pause the video and do it quickly. It doesn't take, just get a sheet of paper and start to solve. It's very, very easy. Okay, I think some people did, some people did not. Let's just go ahead. I think you will catch up with it, but you know that if you have this question in your exams, you'll probably not be confident enough to do it. So just go for it and try to do it and help yourself get confident or good at it. So we now get into it, and you outline. It's good to outline what exactly is what. You know that the number of protons is the 51, the number of neutrons are the 73. So you put that aside and then you try to write it. So this is what it's going to look like. Your X is there, your A, and then your Z, as I said previously. So obviously what it's going to be is your Z is your number of protons, which is going to be underneath, and then you add the number of protons and the number of neutrons, which is above. As I said, the super is the mass, the atomic number is a subscript. The word script is to right, so it means that your subscript is written under, superscript is written above. So that's it for this. So in the next video, we're going to be looking at the atomic masses, and we're going to go on and on. So that's the first part. So look forward to the second part, and I'll see you in the second part of the video. So until then, take care. Bye. See you on the part 2.